Log on, tune in, find out. Another good idea from Cambridge.
Okay, so it's a pleasure to introduce Peter van der Kamp from the Trobe University in Melbourne. We'll talk about periodic reductions of integrable lattice equations, the staircase.
Thanks. I realized it's about a bit more than just the staircase method, so I added some things to the title. I'll start with a bit of the setting in which this work is performed. So we start with a lattice equation, and that's a two-dimensional lattice. Then we impose some periodicity. We assume there is some initial value problem which is well posed, and then what you get, you reduce the lattice equation to a mapping or a correspondence. So that's one thing you can do, and then you can, if on top of this you have a Lex pair for the lattice equation, then you can use that Lex pair to find integrals, and this is done by the staircase method. Now you can ask several questions, such as how many integrals do you get? Are they functionally independent? Are they an involution? Do they generate a complete flow? Can you parameterize the common level set of those integrals? That would correspond to solving really the whole thing. These questions go a bit further than what I can answer, so that in that setting you can kind of think about these things. Then can you do this for arbitrary equations? So just and for systems of equations, how does it work? And you can ask questions about the growth properties of those mappings or correspondences. A bit more specific, what I'm going to talk about is I'll first start off with an easy example, some equation defined on a square or an elementary plaquette of the lattice, and do a particular reduction and show you how you get your mapping. Yes?
Periodicity restrictions. You put them in both variables.
Yes.
So you have x and time.
Yes, so basically you've got your field defined on the lattice. There's 2 points on the lattice which you identify. So you can think of taking your lattice and folding it up into a cylinder, and then look at the evolution on this space, right?
Periodicity restriction was written for both variables.
Both variables.
M and N. Yes.
Yes.
But it's only
yes.
only one.
Is it 2 plus 1 system or 1 plus 1 system?
It's two. There's two variables, L and M, two directions, two-dimensional lattice.
1 plus 1, more or less. Yeah?
1 plus
So
1.
it is elliptic, yes?
Well,
Periodicity.
it's discrete.
No.
Everything.
I mean that it is not periodic problem like periodic Cauchy problem. It's what I don't understand.
No, it is like a periodic
Because
Cauchy
you consider periodicity in both variables, x and time.
Yeah, but not.
This is the lattice,
Yeah.
and now you can just pick your one point on the lattice, and you can identify this point with another point on the lattice. Say this point here. Right now, this is S1, and this is S2. So you're identifying 2 points, and 1 point on a two-dimensional lattice has 2 coordinates. So that's
It's
S1.
1
and
period or 2 periods?
1 period.
One, so it's like Cauchy problem.
Yes.
No problem.
Yes.
I understand it.
So, but depending on what the periodicity is, you get either a mapping or a correspondence in general. So I'll give an example of that. Then I'll show you how you can construct the integrals for this mapping or correspondence. And then I'm going to show you a good way of deriving the mapping and the integral. So there's a particular way of doing things which is particularly nice, and that's called the standard staircase or standard mapping. Then I'm going to generalize, so from an equation on a square we're going to look at other equations and at systems of equations as well. Then I will say something about closed form expressions for integrals and how you can prove functionally independence, involutivity, and maybe if there's time, we'll have a look at growth properties. And these are just some particular examples which I want to show you. So this is the simple setting. We've got an equation which relates 4 points of a lattice, and of course it relates every 4 points on the lattice. So this is a famous example, the potential lattice potential Korteweg de Vries equation, and this is some initial value problem for it. Clearly, if points are given on a staircase like this, then we can calculate this point from that square over there. Once we've done that point, we can calculate that one. So you can basically see if this staircase extends to the upper right and the lower left, then it's clear you can calculate all points there and all points there, and this is a well-posed initial value problem, and every point is uniquely determined. So maybe you don't want to pose infinitely many initial values, so what you can do, you can pose them periodically, so you can this point is now the same as that point, the same as that point, and what you get by doing this is actually you get a mapping. So there's 5 initial values, and you can calculate the next 5 by just shifting the staircase. So this is a mapping. So this point maps to that point, this point maps to that point, and so on. So that's a 5-dimensional mapping, and by iterating this mapping, you can generate all the points in the whole lattice. That's how you get a mapping. Now, if you consider this initial value problem, where you have identified this point with that point, you got 3 initial values, so you get a 3-dimensional mapping. But if you impose now periodicity for the solution, then you can't really use the equation to find one of these values. You really have to solve the whole system of equations. So the image points of this mapping would be these 3 points there, and you can find them by solving this system of equations. There's 3 equations, one on this square, one on that square, and one on that square. So you got 3 equations, 3 unknowns. You can solve that system, but in general there's more than one solution. So that means that the mapping you get is multi-valued, and in this case you can easily show that it's 2-valued. So that's how you get correspondences. Yes, this will give you a 2-valued mapping.
Mappings provided by Abri, which Sasha Veselov developed also. Same. Is it has it Lagrangian discrete? Following Abri method, like Sasha Veselov developed, like multivariate. Yes, it is belong to same category.
A priori, it's not clear that there is a Lagrangian for this problem.
Is it Lagrangian? Yeah?
That's not clear a priori. Maybe you've got a Lagrangian on the lattice level, and maybe you can deduct or derive a Lagrangian on the kind of reduced level. But these are good questions. We don't know a priori.
No, I mean that it is well known that Lagrangian mapping, since Abri first invented them, leads to multivariate maps. That's well known in mathematical physics.
Yeah.
Sasha Veselov considered completely integrable versions of it.
Yes. Yeah.
Yes?
Yeah.
So just my question is, does it directly belong to that category? Probably, yes.
Probably, yes. Yeah, but that's something you want to establish. I mean, if you want to really answer that question, then you've got to answer these questions that I asked in the beginning. I mean, if you want to show that this is completely integrable, for example, you got to find the integrals. You got to find a Lagrangian or symplectic structure. Or there's a lot of work to do to answer your question.
Should be polynomial.
Yeah, yeah. I mean, if you start with an integrable lattice equation, then the answer is probably yes. But if you start with anything else, the answer would be no. That's
Now, for generic system, it should be exponential. Yes.
yeah.
Growth, yes.
So, what I mean by integrable on the lattice level is that there is a lag spare this is a very weak form. You could also say that this equation here should hold if and only if the lattice equation is satisfied. That's a bit stronger, but for our purpose, this will be all right. Now, this equation here, you can view it as two ways of going from this point to that point, and one way would be going up first and going to the right there, and that's basically this product here. And the other way is first you go from here to there, which is that one, and then you go up, which is that one. So basically it's saying if you use these Lex matrices to go from one point to another point in the lattice, then it doesn't depend on the path that you take. And that's general statement. So for any 2 points here, there, if you take any product of matrices from that point to that point, so there's one given here, it doesn't matter which path you follow. So L is independent of the path. L is called the monodromy matrix if you go from one point to another point which has the same, which is, well, a period distance away. The trace of this monodromy matrix is invariant in the shifting the thing over the lattice. So that's how you get your invariance. And then generally these matrices, these Lex matrices, they depend on a spectral parameter. You can do an expansion in terms of that spectral parameter, and all the coefficients are invariants. So now you've got a bunch of invariants, and you want to know, well, are they functionally independent? How many are they? Are they in involution, and things like that. Yeah.
Where
so
was the K hidden in the previous slide? You showed
it wasn't there. It's hidden, but it's. I'll show you where it's hidden. These L's and M's, they depend on a K, and that's just a parameter in the Lex matrices.
If you don't have parameter, you will not have enough number of integrals.
That's right. Yeah.
But it's not a parameter in the equation. It's a
No.
spectral parameter in our.
Yes.
Yes.
Yes. Yeah. It's not in the
As
equation.
usual, it should be
Yes.
spectral. Zero curvature equation.
So now this is what I think the first instance of where this was applied in the work by Papageorgiou, Naev, and Capel. They had a particular staircase, a particular periodicity condition, or actually two different ones. So this corresponds to a staircase, the NN reduction corresponds to a staircase like this, and the other one is one step more at the end. Then other reductions were introduced in this paper here. So there they take periodicity with a huge class of different periods, but the Z1 and Z2 are taken co-prime. So recently we've kind of generalized this. So this condition where these numbers are co-prime is we don't have that condition anymore, and we actually showed that we realized and proved that this monodromy matrix is actually a Lex pair for the ordinary differential equation that you get by performing this reduction. So that's a nice result, and I kind of found a way of more easily describing how these staircases are built, the standard staircases, and this enabled me to generalize this to more general equations than just equations defined on a square, and that's the next topic.
Hierarchy can be also, all hierarchy can be also obtained here in this, contains in this discretization. I mean, hierarchy definites.
What
Do they fit in this?
you can take higher KdV is probably some equation which is defined on a bigger stencil than just a square, right?
Yes, I mean it's a higher order at least.
Yes. So I mean any equation. It's a general result as we will see. So what we saw in this.
The question can be rephrased. Is there a hierarchy also for discrete KDT?
Yes, yes. I think
Oh.
on the same lattice, but maybe higher order. Yes,
Yeah. Is that the case?
yes, it is my question.
Yeah, you
Is it
can-
known or
No,
not?
but the question is, does it add anything new?
Is it
to the-
anybody updated?
Well, you can do it, but does it add something new to the equation? Because twice a shift is still a shift. So in a sense, you don't gain really anything by writing down that hierarchy.
So they look the same, are you saying that?
Yeah. So it's actually this multidimensional consistency, this kind of fact that you can move into other lattice directions. That is really the proper analog of the hierarchy.
So you need higher dimensional lattices.
Yeah. Yes.
Anybody developed?
Well,
Yes, so
multidimensional consistency,
hierarchies, theory of hierarchy. For,
yeah.
for totally discrete.
So what I was going to say, in the previous case, we had to calculate a few points to derive this mapping, right? You first calculated one point, then you used that to calculate the next one. There is a particular nice way of posing initial values. So this is a similar periodicity, and if you pose initial values in this order, then if you shift now by going one to the right and one down, then what you can see is that this point is shifted onto that point is mapped onto that point is mapped onto that point, which is just one point of the staircase. This goes there, so you only have to calculate one new point to write down the mapping. Still a 5-dimensional mapping, but the mapping is easier. And in fact, any mapping that you obtain from such a reduction can be obtained by, can be written as a power of this particular mapping which you get here. So that's a nice way of posing the initial values. You get a fundamental mapping in which all other mappings you could get can be expressed. And now the question is, how do you find for arbitrary S this particular way of posing the problem? And standardly, what is done is to introduce some similarity variable, and then you write down the field in this new variable, and that goes like this. You start at 0, you add 3, that's this number there, then you subtract, because you go down, you subtract 2, so you go 1, and you just continue. There's 4, there's 2, there's 0, so you see the periodicity coming in. It just follows from this particular choice, and so on, and that's how you get your staircase. So you go down here because you can go down without getting a negative number. Then you go to the right, and now you go down again, and at 0 you go down again. So that's how one way of constructing it, and how it was done originally by this variable that basically defines the reduction. There's another way of looking at this staircase, and that's by drawing two lines, by squeezing the square, so to say. So you get your square, you draw two lines in the direction you want you take your periodicity in, and all the points that fit in between those two lines, they give you your staircase, your standard staircase. And now the shift that gives you your standard mapping is just shifting this line parallel to in a parallel direction until you reach the first point, which is that point there. So, and all the points are numbered according to their minimal distance to the first line. So the first line will hit that point, so that's the first point. Then that's the second point, the third point, the fourth point. So that's very well ordered and an easy way to see how these staircases arise. Now this you can generalize to stencil, arbitrary stencils. One thing I was going to say is that in this case the monodromy matrix, which is just a matrix going from this point to the next point over one period, exactly coincides with the initial values you pose. And that's something that you are very used to, and you think this should always be the case, but in fact it isn't, as we shall see. So you can do exactly the same thing. If you have a stencil like this, if you have an equation that is defined on a stencil like that, you squeeze the thing in between two lines, and if you now pose initial values on these black dots, then clearly you will be able to calculate the next point. So this mapping, if you identify this point with that point, is now a 9-dimensional mapping. There's 9 initial values there, and you can update them by moving them in this direction. So it's the same shift again. Yeah, so, but here, this is really different. The monodromy matrix is the same thing. So the monodromy matrix is always on a staircase, whereas the initial values you have to give for this equation, there's a lot more to it. And what you can do, you can find an expression for the dimension of your periodic reduction as a function of your two parameters, S1 and S2. And in this case, this is the dimension. You can kind of check the formula for this particular example. What we have is S1 is 2, S2 is 3, and the max of all these functions is this one. So 3 times S2, the absolute value of that is 9, and that's exactly the number of dots in this kind of parallelogram here.
What do you mean by the sailboat equation? Does it relate all these points in a particular way as encoded by the lines?
Not the lines, they don't have any meaning. It's just saying the lines just express the fact that these points, these 7 points, 1, 2, 3, 4, 5, 6, 7 points are related by some equation. And
the other lines are just to make it look like a sailboat.
yes.
Yes, that is sailboat.
This is my famous sailboat equation, but of course I don't have an equation of this form. But
You wouldn't, for instance, know whether there are any sailboat equations that are integrable.
probably not. But maybe in future we can find reductions of integrable equations to an arbitrary stencil, because I mean, if you have some continuous equation, why would you if you do some discretization, why would you discretize it onto some square equation? Why not on some sailboat equation or something? I mean, or on a triangular lattice. I mean,
But there are 7-point equations known, for instance, within the Bussinesque family.
yes,
And
not of this shape, I believe, but maybe
Well, but,
can be transformed into.
is the shape really that crucial?
No, but the shape is crucial. For example, this formula really is built around this shape. So for every shape you can derive a formula like that. And for square equations, what is the formula for square equations? Well, it's the formula is just the absolute value of S1 plus the absolute value of S2. And that's your formula for square equations, which we all knew, but now we've got kind of some general procedure to derive formulas like this.
But there is also this point of view of Adler, where you can write, for instance, quadrilateral equations on arbitrary graphs, basically, or
Yes.
graphs where
Yeah.
each equation has basically
Yeah.
related to 4 points. And if you could do something similar for kind of 7-point equations, then the shape is not that.
Well, I think that is a very difficult question to both allow the stencil of the equation to be kind of anything, and the graph it is defined on, because you cannot, that's really, I think that's a step too far for that.
The shape has meaning with respect to the periodicity. You would use it on a different, if you were to mess up the underlying geometry, you couldn't play your periodicity values.
No,
Right?
no,
So
that's
this,
right.
This shape
Yeah.
has meaning with respect to the periodicity.
Yes, yes. So periodicity would be
It's really
difficult.
the dimensions is for the square, but what was the dimension again in that case? I mean, what do you mean by dimension?
the dimension is the number of initial values you pose. So for example, for the square, this is a well-defined initial value problem. And if you take periodicity here, then we've got 1, 2, 3, 4, and 1, 2, 3. So it's basically S1 plus S2. That's the number of initial values you pose, and that's the dimension of your periodic solution. So now we kind of know how to do these things for scalar equations defined on arbitrary stencils. Can you do the same thing for vector equations or systems of equations? And here is one system of equation which also has applications and is integrable, as observed by Papageorgiou, Ramani, and someone else. So this is, in principle, a system where you can do reductions and things, but it's not clear a priori how, for a given period, you should pose the initial values. So that's one thing that I looked at. So for example, here is a square, and we cannot pose all the values of the E and the Q field on a staircase like this, because if we would know EQ here, EQ there, and EQ there, then they should satisfy this relation, right? So you cannot give them as initial values. And similarly on a triangle like in this corner, there's restrictions. So there's definitely you cannot pose all the values of these E and Q fields on a staircase. So here is a well-defined initial value problem for this system. And so you give the field the value of the E field at this point, the value of the Q field at this point. You give the value of the E field there. You don't give any value there. You can calculate it, and so on. So how to see that this is a well-posed initial value problem? Well, it's a bit the same as for the scalar case. So what do we have to do to find a mapping? We have to do a shift, and in this case we shift this point to that point, and then this point to that point. So we have to be able to calculate the E value here, right? And similarly, if we do the shift on the Q, we shift this Q, this value to that value, this value to that value. So we have to be able to calculate the Q field there. And once we've shown that we can calculate the E field in this point, the Q field in that point, then we know we can just continue taking iterates of the mapping and fill the whole field, obtain all the numbers. So how to do that? Well, the E field can be obtained from this triangle here, which is that one, and the Q field can be obtained from, once we know the E field there, we can obtain the Q field by using the other triangle. So this is kind of a particularly simple mapping. We only have to use these equations, both of these equations, once to find the mapping. And for this system, you can show, if I've shown that for any choice of S, you can do this, and the dimension of the S periodic solution is given by this formula. I don't have so it's a bit of a puzzle, and I don't have an algorithm to if you give me some system of equations that I can apply and do it as I can for the scalar
S1
case. But
is simply S1 from the to the right.
yes, that should be in
Simply S1.
subindex, yes. So, yeah, but for this system you can, so in any direction you can do this periodicity thing, and once you can do that, then you're in good shape. You can just calculate the trace of the monodromy matrix and derive your integrals for the mapping and study. Yeah, try to find solutions from there. So we have been looking at reductions where there's a parameter in your reduction. So you can look at some arbitrary family of reductions of certain equations. And the surprising thing was that we were able to find an explicit formula for the integrals in terms of multisums of products. And at first, we just found this by just applying the staircase method, multiplying all these Lex matrices, doing an expansion and looking at the integrals, and then you see some structure, and if you look hard enough, you can describe that in terms of these objects. Later we found a better way of looking at it, and this is using a non-commutative Vieta formula. So basically I'll go back for a minute. These objects called multisums of products, they are not that alien. We all know the elementary symmetric function. So if you get rid of this -1 to the power something here, and you just think of this as the roots of a polynomial, then you know that the coefficients of that polynomial can be described as elementary symmetric functions of the roots, and that's basically this formula. And this just gives a little twist to that to the elementary symmetric functions, as we can see, because this is basically, if you think of this formula here as if you think of this matrix as just being lambda, so you replace the matrix and you replace it by the scalar lambda or x, and then you view this as the roots of that polynomial. This is just the product of factors. So yes. Well, this product is over the whole of the. Yes. It's the product of the sum. Yes. So this I is running is the same I as there.
What is the D? Arrow?
I'll write that down. So the arrow from 1 to n arrow of x, I is 1 is x1, x2, x3, xn. So it's just the reverse order of the products. Yes, so if this is a scalar and these are the roots of that polynomial, then you would just get the elementary symmetric functions here. But now we've got these different functions there. These functions, they also satisfy some recurrence formula, just as the symmetric functions. And if you take this as initial values, then these formulas give you a very efficient way of actually calculating these multisums of products. So we've been going on and see if we could find similar formulas for the integrals of the ABS equations, and we succeeded, apart from the Q4 equation. But we had to come up with a different multisum of products And this is, the range is a little bit different, and this funny -1 is not there. So this is, I2 is strictly bigger than I1 plus 1, and that holds for all the variables. And these arise in, if you do a non-commutative Vieta expansion of this product of this sum here, where we don't have a lambda here, right? So that's the big difference. And if you square this matrix, you get 0. So if you have two of these matrices next to each other, then some terms vanish, and that's how you get this plus 1 in there. But yeah, so these play a fundamental role for other equations in the ABS list. And I want to say something about functionally independence of these functions, because now that we have really closed formulas for the integrals, we can think about proving functionally independence of them. And the trick is to use this recursive structure we had on the previous slide, and also this little fact here. The fact that if you look at this function and you take all the values to be 1, then the value of this function is equal to the sum of the number of terms in this function. And that way you get a handle on what its value is, and you can now calculate the gradients, then stick this value in, and what you get is some kind of arbitrary big matrix where you want to prove that this determinant is non-zero. So you have to prove some kind of binomial identity, determinantal binomial identity. And so we've shown that the determinant of this matrix here, where the ij are indicating the entries in the matrix, is equal to this thing, which is a nice identity. And in that way we prove functionally independence of these functions. Some other really nice formulas, I really like them, so I just wanted to show them to you. They're kind of surprising, and if you look on websites about binomial coefficients, they're kind of odd, and I don't know. I found there's a paper of integer sequences and binomial coefficients, a journal. So maybe
it's relations between ordinary binomial coefficients.
Yes, these are binomial coefficients. These are nice relations between them by proving this functionally independence of these functions. Anyway, we can also do involutivity. So if this is the Poisson bracket, this defines a Poisson bracket, and in fact for certain equations this is a symplectic structure for those equations. I believe this is from Sine Gordon, and when you take the periodicity to be even, then this is really a symplectic structure for the mapping that you have. But anyway, these functions that I defined earlier, they are, if you take the even ones as a set and the odd ones as a set, they form an involutive system of functions with respect to this bracket. So they really have nice properties, and yeah. So I have a bit of time, so I wanted to say something about exponential growth of iterates of the mapping. You look at an equation. This is a non-integrable one. It's basically KdV, but I changed this minus sign into a plus sign. This is some periodic initial value problem for it. Now I take A1 to be 1, A2 to be 2, and A3 to be x, which is just an arbitrary choice. And I go calculate the next point. So I first calculate this point, which is A4, and you can look at the degree, which is, so you look at the degree of either the top or the bottom of this fraction. So this is 1, the next point gives you 2, and there is 4, we got 6, we got 10, and things become very big and messy. But this sequence is exponential. It's basically Fibonacci of n divided by 2 and take the floor of that, and then you get this pattern of things. So, but this is exponential, right? By just putting this plus sign in there. If you do the same thing with the minus sign, which is an integrable equation, you have the same initial values, you calculate the first point, the degree is the same. It's 1, 2, 4, still the same, but here is 5, which is different. So some cancellation took place between numerator and denominator. And there we have 7, so it's much slower. It fits on the screen. And this is polynomial growth. Just a simple sign change. So it's kind of thought that the difference between integrability and non-integrability is the growth of these things. And if you take the log of this, you get the entropy. So the entropy vanishes for integrable equations or mappings. Yeah, so last summer in Canada, in Montreal, Jarmo and Tarinta had showed me, gave some lectures about this, and then I asked about the status of these things, because this is generally just obtained by you calculate, you iterate the mapping, you see a sequence of numbers, you fit it with a rational function, and then you can obtain the entropy from there. But that's kind of it's not proven that this growth of degree really goes with this number. It's just an observation, and for the first so much values you get it. But I found a way of really obtaining this thing. And what happens is that if there is one cancellation happening at a certain iteration, then this factor which cancels out, if you look at the greatest common divisor, it appears as a higher and higher factor up the other iterates. So one factor, the multiplicity of that factor will grow exponentially fast, as does the degree. So those two exponential growth, they kind of cancel in some involutive way, and that gives you polynomial growth. So it's not that there is lots of miracles happening. Once one miracle happens, one cancellation is there, then basically from there you can show that this really brings down the exponential thing to a polynomial thing. But, yeah. And then there's a last thing. So we saw that you can get either mappings or correspondences by taking different periodicities. So I took the QD system, I took a very simple reduction which leads to a correspondence. And it's a two-valued correspondence, so the two branches, I call them P and R. So P is very simple, it's just a permutation. But R is a rational mapping, and you can use the stack as method to calculate integrals. So there's 3 integrals for this, for both of these mappings, for this correspondence. And if you look at the growth of the number of images of the iterates of this correspondence, then it goes like this, which is a nice kind of growth. I haven't seen it before, and it's due to basically two relations between the P and the R, which you can see. So R is, so you start from a point, and you have two-valued mapping P and R is always the diagonal ones, and the P's are the straight ones. So if I do, first I do R, and then I do a P, and then I do an R, I arrive at this point, but I could also arrive at that point by doing 3 P's, and that is this relation. And similarly, if I do a P and another P and an R, I get the same value as if I would do R and then PP, which is this relation. So these two relations lead to polynomial growth of the multivaluedness of the iterates. Now this was very simple to prove, because you've got explicit expressions for these two mappings.
Sorry, Peter.
Yes.
In this case, R is this periodic shift, isn't it? Or one of the two is. Which one is that?
So P is the
Oh, the
permutation.
permutation. So,
Yeah.
but you haven't used that fact.
No, no. So in this case, so in this case, this point will be the same as this point, because P is the identity, right?
You don't need that. So
No, you don't need that. No. And in fact, for the so you can do the same thing in in higher dimensions. So if you do this initial value problem where you have basically periodicity along an arbitrary distance, then you get exactly the same thing. A two-valued mapping, you get a permutation, you get some rational expression, which is a terrible expression, but you can find an explicit form for it in terms of these q's, these functions here. And you can really prove these identities, but you have to establish relations like this. So you have to work a bit, but in the end you get exactly the same growth for a 2n-dimensional correspondence as you get for the 4-dimensional correspondence, which I explicitly showed you. And there, coming back to your question there, you would have that not the fourth power of P is, but it's so that the dimension, if you take the same power as the dimension, then you get the identity there.
It is big secret permutation.
Yes. P is a cyclic permutation.
But group is basically the same with this additional relation. Group.
Yeah, so basically you've got a group here, and I've got a representation of that group in arbitrary dimensions. Yes. Are there any questions? This is what I wanted to tell you.
For your integrals, the level surface, is it Lagrangian submanifold? Is it sometimes compact torus? Because it's also so you prove complete integrability in sense that you found just 1/2 integrals. Yes.
Yes,
did you
but
claim
I'm not
it's
there
not
yet.
possible?
I'm not there yet. This is a work in progress. What I want to do is exactly go in that direction. But for some equations, we have symplectic structures for the mapping. So we were able to prove complete integrability in the sense of proving the involution of the integrals.
Is
but
level compact set?
I don't know.
It's level of integrals,
Yeah.
like torus.
I suppose so.
You expect that, but it might be compact or not compact. In
Yes.
good cases, it is compact.
Yes.
But
My guess is that it would be compact, but
Right.
I haven't gone that far yet.
Well, since first of all you would have to show the completeness of the flows.
yes, it's also a question. Yes.
Yeah.
You gave one
Like
example of
Lagrangian
the Poisson
submanifold.
right?
Yes.
Could you demonstrate again? Because there was one equation where it had been done apparently.
Completeness of flow.
Right.
Yes.
This is Poisson bracket engineered such that the Fi and Fj Poisson formula. Is that the idea?
Fi and the F.
Are they
So-
considered to be independent variables here?
These are independent variables, yes. So in this case, my f's, because I defined. Let me go back to the definition of back. I wanted to go. Yes, so here we have our f's. So these functions are just functions of f. So the f's are the variables.
Yeah, and
Yes.
are there, you talked about the dimension of the initial value. So what you would expect is
Yes.
that there might be half, if the dimension is even, half of these Fi's around. How many are
Yes, is it about 1/2? It's, yeah,
Yes,
it's-
yes, definitely, yes, yes. It's about 1/2, and it's always
Same.
plus or minus 1 or 2.
Yes, yes, yes. Like
And in
it's
certain cases, for example, I looked at the Boussinesq system, and we did a reduction, and then we observed that in certain cases we had kind of one integral to less, but then it was possible to introduce new variables. So that you could write down this mapping in lower dimensions, and then you would have enough. But when 3 was a divisor of the dimension, there were 3 integrals to less. So we had to reduce the original mapping, which you get, by 6 dimensions to make sure that we had enough integrals, and we were able to do that reduction by 6 dimensions. So in most cases, I've got one kind of one example of one reduction for a particular system of equations that Frank found, where I have, in the end, when I do all the reductions, I get down to a 5-dimensional map and only 2 integrals. But
Your
it's
puzzle
still
bracket is so puzzling in that sense, because the differentiations are only with respect to the FIs, but they're too few. You need twice as many. You need as many as the dimension of the initial space to have it be a symplectic manifold.
There are that many. It's not the F's that are half the dimensions, it's not the integrals.
Yes.
Oh, okay,
Yes.
okay. So the FIs
So-
are as many as there are variables on your lattice that you can choose independently.
Is your Poisson bracket obviously non-degenerate?
Yeah, exactly.
Maybe it has annihilators. Yes.
If it's an odd
Casimir.
number, then if it's an odd number, it has to have a Casimir.
Yes, yes, yes. Should
Yes.
have Casimir.
Yeah. So in this case, I mean, how many of these functions are there? We've got basically, well, S can run from 0 to P, but from 0 we get a constant. So basically there are P functions, and we've also got, okay, that should have been an N, the P. P is equal to N, right, on this slide. So there are P or N functions, and we've got this, but half of them are in involution. So if you look at either the odd ones, the odd functions, or the even functions, where this is the index, when R is odd, you got kind of half the dimension of the functions that are in involution. So we got 2 sets of functions that are half the dimension of the space as functions that are in involution. Is that clear? Or?
About these Casimirs, if you start from kind of, say, there are a number of cases which are well known, but kind of more arbitrary or situation, is there a way of selecting them or finding out which ones are Casimirs?
Well,
So is this for instance, this is a specific example?
yes.
And which case was this?
I think this was for the Sine-Gordon equation, where you do a P minus 1 reduction. And
But if you start
take-
from your monodromy matrix
Yes.
expansion, then if you just look at all the coefficients of the spectral parameter in the expansion, then some of them actually are Casimir, those coefficients. And can you predict in some sense which one?
So how would you? I'm not sure. How would you distinguish between an integral or a Casimir? What is the?
Well, Casimir annihilates the Poisson bracket.
Yeah. Right.
But
To find out whether
I don't think, I'm not aware that any of those that you get from the expansion are Casimir. They're usually, I think, additional.
Depends how you set it up, because if you already kind of equate from the very start certain things with parameters, which could in principle still be arbitrary functions, but if you set them up to be, for instance, in this reduction procedure that you're doing, you're kind of there you use in some sense you use the fact that some of these things could actually arise first as Casimirs, and then they give you a condition which is compatible with this. I don't know if I'm making sense, but
Yeah, I'm not sure whether that's the approach I follow.
May I ask you a question? Is your formula, if, as far as I understood, you don't develop Lagrangian approach yet, yes?
No.
So you wrote some formula for Poisson bracket. So it means that you simply just wrote it arbitrarily, but it fits your equation. Maybe there are other Poisson brackets. If you have some specific Lagrangians, in that case your Poisson bracket is just canonically unique. But you might have such with Leonard-Magri situation that you might have also second Poisson bracket.
Yeah.
That's why not.
Yeah.
It is not with different Casimirs. Yes.
Can you actually go to Darboux variables by parameterizing the FIs exponentially, for instance? Looking at the signs, whether they work out.
I haven't looked into
Okay,
the
they're not
direction.
Darboux coordinates as they stand, but to me, it seems like there might be very simple substitution.
Yeah.
I think in this case, I think
Yeah, but it seems not to quite work out. Because you get exponentially, you get them twice upstairs.
F5J. This
this is D log F
formula
J,
is
D
not
log
far
F.
from Darboux canonical
It's
form.
not far, but
No, but almost.
if they,
It's only
would be,
product.
if there
only
would be the
product.
denominator, then you could get rid of them by an exponential substitution.
No, it's just Fi D Fi is the D log. So this is substitution gets rid of this, and then it's sort of so it's
Yes,
minus
D
one
log
point.
phi. Log phi
it's a
are
log.
Darboux
It's a
coordinates.
log.
yeah.
Obviously.
Oh, but then you
that's
know
fine.
exactly what
In
your
this
theta's
example.
look like
Yes.
in terms of x and p, and they have the same dependence on x and p in that case. They're exponential in the x's and the p's, so you can answer all these questions.
Mhm.
Anyway, I think we should
Yeah.
It is canonical brackets, so it means
Yeah,
that
yeah.
it comes from Lagrangian. Lagrangian will be nature of this canonical bracket.